You ever just look at a rocket launch and think about how wild it is? These massive, skyscraper-sized machines, and all they're really carrying is that tiny little capsule at the very top. It just seems kind of crazy, right? Well, today we're going to dig into why our gateway to the stars is, for the most part, a giant empty fuel tank. So check this out. This is a classic comparison from NASA. That huge rocket on the right is the legendary Saturn V. It was 363 feet tall. But the only part that actually went to the moon was that little bitty spacecraft sitting way up on top. The rest of it, basically the most advanced, most explosive, disposable packaging ever made. And really, it all boils down to this one simple question. To get something the size of a school bus, or heck, even a car, up into orbit, you need a rocket the size of a building. What's with this insane difference in size? Well, it all comes down to a simple but absolutely brutal paradox of physics.
And that brings us right to the heart of the matter, what we're calling the rocket paradox. It's this vicious cycle that has defined spaceflight from the very beginning.
Okay, this chart right here just spells it all out, doesn't it? When a rocket is sitting on the launch pad, a staggering 90% of its entire weight is just propellant, the fuel and the oxidizer. The actual rocket, the metal, the tanks, the engines, that's only about 6%. And the payload, the whole reason you're launching the thing in the first place, a measly 4%. The rocket is basically a flying fuel tank with a satellite attached as an afterthought.
So here's the crucial part. To go up, a rocket has to shoot mass down with an incredible amount of force. And that mass, of course, is the propellant. But here's the catch. That propellant itself is heavy. So to lift the fuel you need to get to space, you need more fuel, which of course adds more weight, which means you need even more fuel just to lift that fuel. It's a problem that just compounds on itself and gets out of hand really, really fast.
This isn't just some little engineering puzzle that we can solve. It's a fundamental law of how the universe works. It's a principle so powerful and so frustrating that rocket scientists have a name for it: the tyranny of mass. Or, as it's more formally known, the tyranny of the rocket equation.
Now, you do not need to be a math whiz to get what's going on in this graph. That line across the bottom, delta V, that's just how much you need to change your speed to get where you're going. Think of it as your speed goal. The line going up the side is the mass ratio, which is basically how much of your rocket has to be fuel. Just look at that red line. As you try to go faster, the amount of fuel you need doesn't just go up, it goes up exponentially. It shoots for the stars, literally.
And this quote from our source material just nails it. To get that massive kick of speed you need to reach orbit, you are fighting against this brutal exponential curve. Every tiny bit of extra speed costs you an exponentially bigger chunk of fuel, which makes your rocket bigger and heavier for less and less return. This is the tyranny that engineers have to deal with every single day.
So when we talk about that mass ratio on the graph, this is what we mean. It's just a simple comparison of the rocket's weight on the launch pad when it's full of fuel to its weight after all that fuel is gone. The higher that ratio, the more of the rocket was just propellant. For the really big rockets, that ratio can be something crazy like 20-1. But here's where it gets even more interesting. When we say dry mass, it's not just the empty metal shell. Dry mass is everything that isn't propellant used to create thrust. That includes the payload, the structure, sure, but also any leftover fuel sloshing around, and even the crew and their supplies like oxygen and water. At the end of the day, physics doesn't care what the mass is, it all has to be pushed.
So if you're trapped by this tyrannical equation, what do? You can't change the laws of physics, so you get clever. Engineers have figured out some pretty brilliant ways to kind of cheat the system, and that's what we're going to look at next.
The most brilliant solution, honestly, is multi-staging. Think about it. Why would you carry a massive empty fuel tank all the way to orbit? You wouldn't. As you can see here, you use a giant first stage to get off the ground and through the thickest part of the atmosphere. Once its fuel is gone, you just drop it. You get rid of hundreds of tons of dead weight. Then a smaller, lighter second stage fires up. Its engine now has a much, much easier job, pushing a rocket that's way lighter. It's the ultimate example of packing light for a very, very long trip.
So once you've figured out staging, the next battleground becomes the rocket's own body. And as this quote points out, the biggest pieces of that structure are the giant propellant tanks themselves. So making these tanks lighter is one of the absolute best ways to make a rocket more efficient.
And you can see that evolution right here. For decades, rocket tanks were made of metal alloys, but the future is in advanced composites like carbon fiber, which you can see on the right. This stuff is incredibly strong, but way, way lighter than metal. Shaving just a few kilograms off the rocket's dry mass can mean you need tons less fuel at liftoff. Every gram counts. Now for a truly wild example of lightweighting, you've got to look at the balloon tank. This was used on the Atlas rocket. These tanks were made of steel so thin that they had no structural support on their own. They literally had to be pumped full of nitrogen gas just to keep from collapsing under their own weight. I mean, it sounds completely bonkers, but it just goes to show the extreme lengths designers will go to save every single gram of mass.
Okay, so staging and lightweight materials are amazing, but they're still just working around the problem, right? They're coping with the rocket equation. What if we could break free from it completely? Well, that's where we have to look to the future of flight.
And that's the big one, isn't it? The question that drives all the advanced propulsion research. If we ever want to really explore the solar system and go beyond, we might need new technologies that don't depend on carrying these enormous tanks of propellant with us.
And here are just a couple of the ideas being kicked around not for launching, but for moving around and braking in space. A drag sail could use a planet's super-thin upper atmosphere to slow down without firing an engine. A plasma magnetoshell could create a magnetic bubble to do the same thing. See, these ideas are all about using the space environment itself instead of just fighting it with brute force. They hint at a future where our spaceships are no longer defined by the giant fuel tanks they have to drag around, but by how cleverly they can travel light.